Hi again. We are going to either wrap up or come close to wrapping up my initial remarks on relativity by starting with some invariants. As I mentioned before, Einstein actually regretted calling his theory the theory of special relativity because what's often important to a physicist and important to a scientist is what's invariant, what doesn't change, what is conserved. We already know a couple of these, speed of light and the laws of physics in an inertial frame. And here I introduce another, the space-time interval. It's a way of measuring the separation between events. But now instead of using a ruler, we have to use a ruler and a clock. Right? If you consider a light pulse that moves out in a sphere, you can compare how fast it's moving times the time it takes to move, say c times delta t squared, and that will describe a distance, say delta x squared plus delta y squared plus delta c squared. This is more intuitive than you think. We had previously measured distances by looking at the difference in x and y and z squared and added those together in the square root, and we called that a length. We can also do that for the primed frame. That is, from the point of view of a frame that's moving with respect to a frame that looks like it's at rest. There we're just using the prime coordinates. And it turns out that those will give you the same answers. That is, we can identify in what we call a space-time interval, delta s squared. And we still use the square here because sometimes this value can be negative. And it looks a little weird, I understand, but the neat thing about this is that this is conserved. This is the same whatever reference frame you're in, okay? And that is c squared times delta t squared, so if you measure the time at for two different events, minus that change in length, so delta x squared plus delta y squared plus delta z squared, that quantity, that delta s squared is the same in every frame. It's invariant. And we can actually look at this and define a couple of, well, three different regions. So if delta s squared is greater than 0, right, that means that this is less than that. We call that time-like, right? And if delta s is if delta s is greater than 0, this is time-like. Clearly t dominates here, delta t dominates here. If delta s squared is less than 0, this is bigger than this, and we call that space-like. And if delta s squared is equal to 0, we call that light-like, right? In other words, that's the interval between two things in which light is traveling between event 1 and event 2, okay? And it turns out in terms of a light cone, right? If you remember, the light cone is this region in space-time, right? We can't access this area. We can't access this area if we're sitting right here, right? These lines are the demarcation. This is the light-like line, and if this were 3 dimensions, this would circumscribe a cone, or 2 dimensions, I should say, right? That's why we call this a light cone. And inside here, we can look at what is causally connected. Outside here, nothing's causally connected. And you should convince yourself where are events time-like and where are they space-like. Okay? Are space-like events outside or inside the light cone? Right? Are they causally, or can they be causally connected? And the same with time-like events. Okay? And in fact, you have your answer right away, unless you pause to think about it. Along this line, we have something that would describe light. That is just something that communicates at the speed of light, so just photons, basically. Inside the light cone is time-like. These events can be causally connected. Outside, they're space-like. Now, let me ask you something. If things are causally connected, will the order of the events change if you move from one frame to the other? The answer is no, right? If things are causally connected, then one that affects two, that affects three, has to happen in that order. Now, they may be spread out in time. They may occur at different positions in space as measured by a moving frame of reference. But if one affects two, then they can't swap places. That's why we call this region inside the light cone time-like. Over here, they cannot be causally connected to, because in order for one, say that's sitting over here, to affect two, to affect three, you would have to have information traveling faster than the speed of light. It's for events that are separated by space-like intervals in which simultaneity can be relative. Here, right, if they're causally connected, they can't be simultaneous, right? The order won't change, but the timing will change or could change. Here, the order can definitely change depending on what frame of reference you are. And then, of course, this is a special line that occurs only for light. Okay, it's a way of dividing up space-time. Something that we already did, but we're getting a little more specific with this. And you'll notice that I'm using perfect differentials. Ultimately, if you were to go further along with this, you would look at how you would do more complicated math in space-time itself. Okay. And you have a clock, and you have a light bulb. You're going to measure basically how long it takes for a light to go from a light bulb down to the floor of the train and back. Okay, you're in the moving train, your time t prime equals 0, the light leaves the train. Okay, you're at rest inside the train, so all you see is light going down, hits the floor, and bounces back. And you time that. Now you know that the distance from the light to the floor is, say, d. So the total distance that the light beam traveled was 2 times that, right, from the ceiling to the floor, and then back again. But we also know that the speed of light is c. So if you're in the train, you would say light requires a time t prime of distance divided by velocity. Very basic, almost kinematic. Ooh, that came back. Of 2d divided by c seconds to reach the floor. Okay, take a second to convince yourself that that makes sense. It's basically something's moving a particular distance, and it's moving at a constant speed. And so the time that it takes to go that speed or that distance is 2 times that distance divided by its speed. Okay, now, what if you're on the station platform and watching the same thing? You're looking into the train and you're trying to measure how much time it takes for that light. This is basically a light clock, right? So now, we put Albert on the platform and he looks in. Because the train is moving now, and we have to, if we're very careful, we actually have to have an array of clocks that are measuring things. We have basically rulers and clocks all over the place, right? As the train moves, the light starts heading down. You can see that the light is actually now traveling a slanted line, hits the floor, reflects back up. Ta-da! Now, if you are Uncle Albert and you want to know how long it took light to go from the light bulb to the floor of the train and back again, that is, you're looking in the train and you want to know, and you're trying to communicate to that person in the train, this is how your clock is running, you would say, you would say that it would be that the time that it took was this distance plus this distance divided by c. You're not allowed to add the velocity of the train, right? And clearly this distance is longer than this distance, and this distance is longer than this distance, right? So the time it took to go down and up again, as seen from the platform, is longer. To someone on the platform measuring that effect, the clock runs slow. And this is not just an optical illusion or an effective perspective. It's actually a physical reality, part of physical reality of motion. And you can show this mathematically. This is how we can get to our gamma factor. We know that the length, we'll call this L, that is traveled, let's just consider 1/2 of this trip of the light beam going down. So this is, we're just isolating the light coming down from the light bulb to the floor. We know this distance already. D is equal to C times T prime. We just solved for that a couple of slides ago. We know this distance is L, which is the speed of the train, times T, because you're measuring it from the platform. And this is just the hypotenuse of a right triangle. So it's the square root of D squared plus L squared, square root. Okay, we'll call that capital D. But we know that C is equal to capital D divided by T. Capital D is equal to little d squared plus L squared, square root, divided by time. Right? So C squared is equal to D squared plus L squared over T squared. What we want, though, is to get a relationship between T and T prime. So let's solve for T squared. That's easy enough. T squared is just equal to little d over C squared plus VT over C squared. This should start to look familiar now. We see that there's a T here and a T here. So all we're doing is factoring out this T squared and this T squared. So we have T squared times 1 minus V over C squared. That's 1 minus beta squared is equal to D over C squared. But we know that D is equal to C times T squared, or T prime. So we can substitute in for D over here. The C's cancel away, and we end up with T prime. So as measured from the platform, T is not T prime, but T prime divided by 1 divided by the square root of 1 minus V over C squared, or gamma times T prime. And as measured on the train, if we wanted to convert from T prime to T, it's T times 1 minus V over C squared. Now notice V over C is always going to be less than 1, right? So this quantity is going to be 1 minus something less than 1, right? So this is going to be a larger time, and the way we write that then is that T is going to be equal to gamma T prime. Okay, and it's this gamma factor that tells us what the time dilation is going to be. T, as measured from the platform, is going to be larger than T as measured in the train. A moving clock is measured to run slow. And that is something that we have seen experimentally. Okay, so just to remind you, go over this again because this is extremely important. T is the time in the train as measured by the platform observer. Okay, whenever we talk about time and distance, we have to locate who's doing what. So T is Albert on the station looking in the train and telling the person in the train, hey, your clock is running slow. T prime is the time in the train as measured by the train observer. That's the guy in the train looking at his watch saying, no, my clock is running just fine. And because gamma is always greater than 1, T is always greater than T prime. that is, moving clocks run slow as measured from outside. Now the question you're going to ask, I can hear it already, is who is right? And the answer is, just as in the case of Galilean transforms, they're both right. And in order to reconcile the differences of their observations, you need to use the Lorentz transformation. And the version of Lorentz transformation, right, is this time dilation effect that I've written up here in equation B.1 and B.2. Okay. Another way of writing this, of course, I've already drawn this, is t is equal to gamma times t prime, or t prime is equal to t divided by gamma. Remember, t prime is measured in the train, but if you wanted to compare it to what the person on the platform is saying, you would take their time and divide by gamma. And basically, you would get your own time back. Right? This is, again, another depiction I just placed on the website of Minkowski or space-time diagram simulator. I want you to play around with that. It'll be useful for lab and for some of the homeworks as well. If you want to measure the position of an event in space and time at rest with that event, then you just read off from this rectangular grid. If you're measuring from a moving frame, then you have to use these tilted axes, and you're measuring x prime so that it's parallel to this vertical axis, and you're reading off t prime so that it's parallel to the horizontal axis. And that is at the heart, graphically, of all of these transformations. Okay? You're going to see gammas a lot, and again, V over C, we often call beta as well. Okay. As I mentioned before, this is not just an optical illusion. We measure these things. Right? We measure them by comparing atomic clocks, one that is, say, on the ground and one that is flying in a plane. And we can tell that the clocks become unsynchronized, that one tells time slow compared to one that's not moving. We know that muons that are created in the upper atmosphere from cosmic rays that strike the atmosphere and are created in the upper atmosphere have a particular lifetime before they decay into smaller particles. They would not reach the Earth unless their time, as measured from the Earth, was dilated. The fact that we can measure these muons, this muon flux, these particles reaching the surface of the Earth, is because the time that we're measuring has slowed down for them. So we can measure this. We see natural examples of this. This has been confirmed experimentally. As weird as it sounds. Now, you can well ask, and you should be thinking, well, if the time is measured from us is slowed down, it hasn't slowed down for the muon, so how does the muon get down to the ground? That's a very good question, student. From the muon's perspective, everything shrinks. And so there's another effect of relativity called Lorentz contraction, in which moving rulers appear or are measured to shrink. And so from the muon's perspective, it has less to go before it decays. From our perspective, it has more time to go before it decays. In both cases, we can reconcile those differences and the fact that we actually measure muons at the surface of the Earth. But for now, we're talking about time dilation. What you need to know is that t prime is equal to gamma t. Moving clocks are measured to run slow, and it depends on the speed of the moving clock. Okay, well, what about the twin paradox? You've probably heard about it, and I think your book writes about it. And the idea is, suppose you have two twins.